So I am Veelasha Moonsamy. I'm currently a postdoc in the digital security group at Radboud University in the Netherlands. And this talk is some work that I've done since the beginning of my postdoc. So the idea or the plan I had was to start with the categorization system that we came up with for Sidechannel attack on mobile devices, and the end more part was actually to present one of the cool attacks we did on Android phones. So instead, I'm going to flip it in reverse and then start with the end more part. So the end more part, so the cool project that I'm referring to is something we did, which is looking into how to establish a covered channel using a USB charging cable. So some of you might already be thinking, oh yeah, of course you can already transfer data through USB charging cable, but there is a surprise there. So how to establish a covered channel using USB charging cable on mobile devices. So through this, I would like to give you an intuition and also motivate why we need a new classification system for side-channel attacks on smartphones. And hopefully, by the end of my talk, I will be able to convince you that this is indeed the case. So basically, my talk is outlined as follows. The first part will be presenting the attack, and then the second part I will move into generalizing all side-channel attacks on mobile phones and present the new categorization system. All right, so let's start with part one. So this is basically a copy and paste of the title of the paper, which I thought was really cool. So it says no free charge theorem. So as you can see, it's a pun on no free lunch theorem. So you would understand in a bit why. So essentially, the idea is to build a covered channel via USB cable on mobile devices. So the motivation, before I start with motivation, I should acknowledge this collaboration. This was a work done together with the people at University of Padova, University of Washington, and myself at Radboud University. And the paper is online on arXiv and will soon be published as well. So it has been accepted for publication. All right, so the motivation. So I think I do not need to convince you all that there is an increasing use of smartphones, and this is also giving rise to what we call battery draining apps. So apps are becoming more and more fancy. Users are spending more and more time on their phone. As such, they are quickly running out of batteries. So phones are becoming very powerful, and the flip side of this is that they're also running out of battery quickly. So you've all heard about one of the latest craze, which was Pokemon Go, where people were just roaming around and looking for those little Pokemon and capturing them and fighting them. And this, as a result, was also making their battery or draining their batteries on their smartphones. So in fact, what was happening in the Netherlands, on the Dutch trains, the people who were selling teas and coffees were actually also selling power banks at that time, because it was such a good business that they knew people would be out of battery and they would desperately want to recharge their phones, so they were selling power banks at the time as well on the Dutch trains. So this also leads to what we've heard from the previous speaker, something called nomophobia. So I didn't know about that term until recently, so a few hours ago. So, which means that you will not be able to use your mobile phone, and it's apparently a health hazard as well. So this was where we started thinking, okay, so what happens when this is the case? So people will eventually turn to free charging stations. So during my talk, I'm going to interchange between public charging stations, free charging stations. I all mean those towers where you can plug in your phone, and there are already USB cables available. So this is nowadays a common sight at airports. You can recharge your phone in airplanes. They have USB ports there. You can do that in shopping malls. You can do that in museums, at the gym, in your hotel room. You can charge your phone overnight. So It's pretty much everywhere nowadays. And it's also becoming an emerging business model. So wherever the money flows, that's where the business will follow. So in the US, it's quite popular nowadays to have these towers in shops, where people would go in the shops, and while they're browsing at articles or products, they would then just lock in their phone into those little slots here. So you can see if a slot is being used, it will be red, so they're given a PIN code, and then they will type the PIN code to open the little box here and then take their phone out. And then at the very top here, you have space for advertisements. So not only you're getting free power, but other businesses can advertise their products here as well. So I think this is something that will also appear in Europe. If it's making money in the US, it will eventually find its way here as well. So we said, all right, what happens if those towers are actually compromised? Because we are nilly-willy just plugging in our smartphones, our devices into those towers, and then assuming, oh yeah, obviously I desperately need it to recharge my phone, and that's what I'm going to get from this. So the question that we asked ourselves was, is it possible to exfiltrate data from a device while it is connected from a public charging station? And the answer is yes. So how did we do that? So I will start with our contributions before giving more details about the attack. So in order to perform the data exfiltration, what we used is the power feature of the USB charging cable. So irrespective of whether you cut the data pins in the charging cable, as long as the phone has current going through it from the USB cable, the attack works. So we showed that it is possible to use power bursts to exfiltrate data from the phone and then pass it on to the public charging station. To do this, we had to build a proof of concept app, which I'm going to refer to as PowerSnitch. And PowerSnitch essentially communicate information in form of power bursts from the phone to the adversary. So the adversary in this case is the public charging station. And then at the public charging station side, we had to implement a decoder. So this decoder is sitting on the adversary side, and what it is essentially doing is collecting all those power traces, and which will then be decoded into binary information and eventually into text. Okay, so we have to set up our attack, so we're going to assume a couple of things. So here on the adversary side, so it's the energy supplier side, we assume that that person or the attacker has physical access to the power meter, so it has been tampered with, and that they are able to monitor and store energy traces via the power meter. And on the victim side, we assume that he or she has installed the PowerSnitch app. So in the previous talk, there were already a few pointers on how you can provide piracy to fully packaged apps. So you can do that through social engineering. Nowadays, if you go to museums, they ask you, if you do not want to pay for a tour guide, you can install our app and then give yourself a tour via the app. I mean, you can have all these kind of scenarios where you repackage the app, profile your target, and then make sure that you know what they need is out there and it's in the form of that app. So that can be done through social engineering. So the features of PowerSnitch, what it does, it will require access to private data, and it does not rely on any traditional permission to transmit data. So here, once again, we're not transmitting data through Wi-Fi or Bluetooth, so, which means we don't even need internet permission or any form of special permission for the attack to take place. And note that to have access to private data, it's not considered as being a malicious information flow, because it's legitimate to ask for permission to access the contact. So again, all in the clear here. So here's an overview of the attack. So on the left side, you have the victim's phone. On the right side, you have the decoder. So that's where the public charging station is. So essentially what's happening here, you have the victim's private information, which is being encoded by the PowerSnitch app. So of course, it's already the phone is already connected to the charging station via USB cable, and it's being charged in the background. So here, Power Snitch will then encode the information, send it to the public charging station. It will be decoded and then retrieved on the adversary side. So in the next few slides, what I'm going to do is first start with Power Snitch apps, explain how it is built, how it's designed, and then move on to the decoder side and tell you more about how the signal, the power bursts are processed. So Power Snitch app. So this is the app that we use to establish the covert channel. So here, we refer to a covert channel as a secret channel that can be used to exfiltrate data from a secured environment in an undetected manner. So note here that I do have secured in between quotes, because this is all happening in a secured environment. So it's not a malicious app. It's legitimate for it to talk to outside entities via the USB cable. So none of this will be detected as malicious. So this Power Snitch app can be deployed as a standalone app, which means you will install it as any other app. Again, permissions are not going to raise any flag because they do not ask, or the app doesn't ask for unnecessary permission, or it can be installed as a library in a repackaged app as well. So how to provide Power Snitch with stealth mode, so how to make it go undetected. So basically, it runs as a background service. So on your phone, if you really go in the lower layers, you'll see there are many services that are running in the background. For example, if you have a weather app, it's going to ask for requests for update, for weather update. So that's an example of a service that could be running in the background. So this will also be one of the services that could be running in the background. So how do we make the data exfiltration happen? So to do that, we use the wake lock permission. So again, not a permission that's going to raise any flag to anyone. So we use the wake lock permission to wake the CPU up if it goes into sleep mode. So usually they do that to prevent your battery from being drained. And then once this kicks in, then we start transmitting the phone, because usually you would assume that if you plug your phone in, let's say if it's in a hotel room, you're going to go to sleep, and then you need to somehow reactivate the phone to start the transfer of information. So this also works even if you have authentication mechanisms. So for example, PIN, or you have to have a pattern, unlock pattern to unlock your phone. So none of that interfere with the data exfiltration. So the phone can be locked, the phone can be at sleep, and it will still exfiltrate data. And moreover, we do not use any conventional communication to exfiltrate information, even if the phone is in airplane mode. So you could be flying, your phone could be in airplane mode. Again, because we do not use internet permission, we don't use Bluetooth or Wi-Fi, NFC communication to transmit the data. So this should all work even in airplane mode. So you are on the plane, we can still exfiltrate data from your phone. And it also, as I mentioned before, defeats the existing USB charging protection dongles. So there has been attacks shown that if you plug in a USB, you could deploy a rootkit that was done on iOS platform. And one way that Apple responded to that was to always use the trust, don't trust mechanism when you plug in your phone to your computer or to a power source, to make sure that, okay, you give authority or authorize charging to take place or information transfer. So this has nothing to do here, because we need power, and you need power, and we will use that to exfiltrate data. So more in-depth description about the app. So it has three main components: the payload encoder transmission controller burst generator. So here we have the payload, so whatever you want to exfiltrate gets sent to the payload encoder, and then the payload encoder will then send it to the transmission controller. So the transmission controller is just there to do a check, okay, is it all right to start transmitting or not? So essentially, it's running as a background service, so kick in the service will start, or stop the service. It can be optional, because if you find yourself being detected by another entity, you can go into stealth mode. And you also want to check the battery, whether the cable is plugged in or whether the screen is on or off as well. So because we want to make sure that the user doesn't get overly suspicious if they are using the phone while the data exfiltration is taking place. So you can request for all of these updates. And then once we are OK, we can then start generating the bursts. So later on, I'll show you more graphics where you can really visualize, OK, how different it is when a 0 and a 1 are being transmitted, and how you can then decode the data at the other side. OK. So here, and on the victim side, you would start the Android daemon. So this is like another view of Power Snitch app, another view into the Power Snitch app. So you encode the private information into binary, so 1 zeros. So here it's up to you how creative you want to be. The device, you can wait for the device to be plugged to a power source, whether it's full charge or not, it's up to you. You can wait for a signal from the accomplice power source to say, OK, yeah, we're ready to start receiving data, start the exfiltration process. And then you start data transmission. So here you can see when the data is encoded, so that's your 1 and 0s, and then what happens when you generate the power bursts, you can really see here that a 0, there's no peak, and a 1 is a peak. So that's essentially how we basically abuse signal processing and power analysis to do this attack. And then from time to time, you also want to check if the USB cable is unplugged. If it's not unplugged, you continue data transmission, or if data transmission is completed, you then go into stealth mode. So stop the service, and then you go in the background. So at the decoder side, so now we're going to move to this side. What the decoder will do, it will wait for the device to be plugged in. And then again, just because you want to make sure that you're not overworking the power charging station, you can check whether there's a Power Snitch app installed on that device, because you do have access to that information. And then you can start recording the traces, so really the 1s and 0s that will be sent. And then you can do two things. Either if the USB cable is unplugged, then or data transmission is finished, you stop. On the other side, you can decode the energy traces to retrieve the private data. So the decoder design consists of these. The decoder consists of these components. So you have the encoded bursts at the very top. So this is what is sent by Power Snitch. Then we're going to do some signal processing, so basically filter the data, threshold estimation, peak detection, so really see where the 0s and 1s are, and then do robust decoding, and then you get the private information out. So I'm going to go through each of those components to give more description about what they are. So in the data filtering phase, so essentially the received signal is going to be passed through a low-pass filter to get rid of high-frequency noises. So as you can assume, on a phone, you have a lot of noise. So coming from apps running on the phone itself, or whether there's other things that are influencing with the power traces, etc. So we do the data filtering to make sure that we have a smooth signal to move on to the next stage, and then we apply a threshold-based detection to make sure that we can get the peaks easier. So anything that basically that will fall below this range, we will consider. Anything below or outside, we will consider as redundant. So this threshold really comes from trial and error. So you have to really study the signal and then see, OK, well, how far you can put the low bar and the high bar, and then consider everything in between. So here you can see an example of a raw received signal here, and then what happens when you apply the low-pass filter on it. So you can see clearly where the 0s are and when the 1s are happening. So second and third components. The second one is the threshold estimation, and third one is the peak detection. So again, here we're looking for a presence and absence of a peak. So anything that's between the threshold, whether it's no peak or low peak or high peak, we're going to convert it to 1s and 0s. So yep, this is what I've just told, otherwise we consider it as noise. So we make a use of a start and end transmission preamble, because otherwise you will not know when data exfiltration started and where it ended. So this is up to the attacker to design how they will notify the adversary to say, okay, this is the start of the data that you need to consider, and that's where it ends. So we make use of that to indicate which peaks we need to consider while considering of decoding the data. So some results, you have more details in the paper, so I would encourage you to take a look at it, but just to give you an idea of what we recovered, so we considered 4 devices, so Nexus 4, 5, 6, and Samsung S5. And here we were transmitting a payload, so from the device, comprising of letters and numbers, so it was a total of 512 bits. So here we present the results in terms of bit error rate. So the lower the BER, the better the quality of the transmission. So you will see here there are a couple of zeros, which means we were able to recover the 512 bits without any errors on the adversary side. So you might ask, why are some of the numbers very high? So we did something that was very basic. So there were no fancy tricks, no fancy signal processing algorithm applied, no error correction. This was just done to show that it can be done. But as you refine it further, of course, those large numbers will decrease. So, and we also suspect that the power meter that we were using might have had noise in it as well. So that could be one of the, some of the reasons why we think the numbers are high there. So you can make power snitch more incognito. So how to do that? So since we're dealing with power here, or power bursts, we want to make sure that the device doesn't get overheated. So to do this, you keep the duty cycle under 50%. So this will make sure that if the attack takes place during battery charge phase, the battery will take more time to recharge if it has a high energy being consumed by the CPU, so hence the user might get suspicious as well. So we want to keep it all sort of at a normal flow. And then, excuse me, there is the Android debug bridge. So here, it is possible for the phone or someone to plug in the phones to use the phone in Android debug bridge mode, so ADB mode, and they will be able to monitor the CPU power consumption. So it turns out we can get easily out of this as well by making use of the settings global ADB enabled on the Android provided by the Android framework to make sure that we know that ADB is running or is activated. Now, so this was just one slice of the pie, essentially. So I'm sure, or if you've not heard of the other Sidechannel attacks that keep coming up randomly, so it might have started, or it indeed started in the early 2010, 2009, where people started exploiting the hardware and software features on smartphones to realize that you could get secret keys, for example, for crypto operation, or information, so private information out of those boxes. So what we realize is that those Sidechannel attacks, so for those who are not familiar with that term, these are essentially attacks that exploit information leakage from computing devices implementations. So think of crypto implementations to infer sensitive information that are stored on the device. So here I've selected randomly a few work just to give you a flavor of what's out there in terms of Sidechannel attacks. So it started back in 2010, so this was one of the very early work. So the paper titles are quite self-explanatory. So if you do a quick Google search for Sidechannel attack on smartphone, these are the results you will get. So you can see here that anything from exploiting sensor information to even recently your Wi-Fi signal to retrieve password used for banking applications. All of these are now possible using side-channel attacks or via side-channel attacks. It goes even further. So nowadays, people are all into wearables. So there has been work done to show you that you can exploit your smartwatch. And it can be used to infer keystroke, to do keystroke inference attack. And recently, there was another paper published, a few years ago in 2013, that studied the crypto implementations in Android applications. And if I remember the numbers correctly, out of 11,000 apps that were studied, 88% had at least has at least implemented crypto incorrectly, so made at least one mistake in their crypto implementations. Now just think about this. All these devices, all these apps are out there being in use, and they also give numbers on how many number of downloads for these apps they were able to find. And there has been attacks shown that with incorrect crypto implementations, you can do side channel to get keys out. So the landscape is changing. So myself together with a few people at TU Graz, we then thought about the problem. As we said, okay, there are people coming up with all these attacks on mobile phones, but no one has really defined this new paradigm shift. So side channels started for embedded system or on smart cards, but now it's getting more and more popular on smartphone, or if you want to generalize it, for smart mobile devices. But no one has really put everything together and really understand, is there any similarities? Where is the trend going? Where are the holes? What are people going to come up with next? So this is what this paper is about. So it's essentially a survey that brings all the side channel attack papers together and really understand through this new categorization system, or what we refer to here as classification, systematic classification. We really came up with categories that show you, okay, where the attacks are coming from, how the attackers are attacking, and in what space it is happening. So at the end of my talk, I promise you, you will have a graphic that will show you the landscape of side-channel attack on smartphone. And of course, the paper is available online as well. So traditional side-channel categorizations are twofold. So you have active versus passive, and invasive versus semi-invasive, and non-invasive. So this is what the categories that have been used for embedded systems and smart cards. So what we mean by active and passive, so you have here your attacker, how extensively it's influencing the behavior of the device. So if it's actively influencing it, it's an active attack, or if it's passively, so only observing leaking information, it's a passive attack. So second one, invasive, semi-invasive, and non-invasive. So here it really depends to what extent you are interfering with your chip in this case. So for example, removing the passivation layer of the chip would be considered as invasive. Depackaging only the chip is semi-invasive. If you're not manipulating the chip at all, it's non-invasive. So these attacks required the attacker to be in physical possession of the device, but nowadays, before I jump to the smartphone area directly, there are a few steps, and those few steps are essentially smart cards, embedded system, and there was cloud in the middle before we moved to smartphone. So this transition really went through smartphone, embedded system, it went to cloud environment, where we saw that there were fewer invasive attacks, so most of it was happening in the cloud, for example, cache timing attacks or DRAM row buffer attacks through remote execution, and then eventually it went onto smartphone. So here we will see that more of the recently published side-channel attacks are mostly from passive attackers, and we would also stipulate strictly non-evasive ones as well. So what are really the causes for side-channel attack to take place on smartphones? So here we defined what we call the 5 key enablers. So of course, your smartphone is always on, you're carrying it everywhere. Businesses will allow you to bring your devices to work, so that's the whole BYOD phenomenon. It's very easy to install any and every single app that you want. And it's based on a Linux kernel, which was not originally designed from the very start to be a smartphone platform. So it has been transported from a desktop to a smartphone platform. And then, most important of all, you have a plethora of features and sensors that come in those boxes, and God knows what information it can leak all over the place. So here, what we found is smartphones are essentially vulnerable to, if not all attacks that are existent in the smart card and cloud computing environment. And this is because mostly enabled by the 5 key enablers that I mentioned before. So before I move on to the categorization system that we proposed, I'm just going to fill in another gap here, which is to really show you to what extent smartphones is overlapping with smart card and cloud side-channel attacks. So here on the y-axis we have what. So what is it attacking? Is it the hardware or the software? And then on the x-axis, how is it attacking it? So is it through physical presence or software only, also through remote attacks? And you can see the grid in red denotes smart card, the one in green, it's for cloud-based attack, and blue is essentially smartphone. So we're going to zoom into that figure later on to really show you what the actual attacks are. So through long discussions, we came up with 3 categories. So again, moving away from the traditional side-channel categorization here, we said, okay, let's look at it from these 3 categories. So passive versus active, physical versus logical properties, local versus vicinity versus remote attackers. Can we, through those 3 categories, really embody all the attacks that are out there, and also be able to see what future attacks will be like? So here I'm going to really just go very quickly. So all the details, once again, are in the paper. So passive versus active, that's the same as for the traditional side-channel category. So physical versus logical properties. So really here, are we exploiting hardware or software features? So that's the difference between the 2. Local, vicinity, and remote. So here for local attackers, we mean, are they in possession of the device? Vicinity, is it a network-based attack? So you could be anywhere eavesdropping network communication. And remote attack, it's really software-based execution on a targeted device. So we then came up with this grid. So essentially, on here you have the attacker, so what kind of attacker it is. So here the side channel vector, is it a physical property and or a hardware property? Physical property or logic property. And then here we have for active and passive attacks. So you can see these duplicates here. And if you plot all the attacks, I'm not sure if you can really see that properly, but in the paper you will have a good view of what the figure looks like. So the dots in red are active attacks, the one in blue are passive attacks. And then you can see here that we've incorporated the grids again here. So red attacks are smart card attacks, and green ones are cloud-based attacks. So they're not all, but it overlaps with the ones on side channel on mobile devices as well. And you can see here that there are clear areas where a lot of attacks are happening or taking place. And this also help us to see that where the blanks are and what we can foresee in the future. And by extension, also come up with countermeasures. So with this, I'm going to conclude my talk and leave you with this slide to think about any future research that could be done in that area. And I thank you for your attention.